let's see. Yeah, it's working. So
I can check on my phone. Yep. You alright?
yeah, so I'm also gonna drop the link on Discord. And where else we can drop it?
Audio is working. Sounds good.
So I think everything is ready. We can begin now.
Did you switch to presentation view?
Yeah,
I think it's okay.
so can you see it? Oh, wait, I forgot to switch.
It's not presentation view.
Yeah. Now.
It takes a few seconds.
Yeah, it should be correct now.
A few seconds. More than a few seconds. Yep, okay.
So it's gonna go full screen right now.
Yep.
So I think we're ready to start.
Yep.
So hello everyone, this is the July meetup of Lisp Ireland. We are a group of people that are interested in Common Lisp and other related languages like Emacs Lisp, Scheme, Clojure, whatever else. And so I'm your host today, and we're gonna have a presentation called A Tour of Common Lisp, where I will go over each major feature of Common Lisp and show some examples of how it is used generally. So this is also the introduction of the topic of our group, and I'm gonna talk about the language itself and ecosystem, like the libraries, the editors, the build systems, etc. won't be part of this presentation. I will cover that next time. And also I will try not to go into history too much, even though it's my favorite topic. But there will be some history anyway. So yeah, what is Common Lisp? Common Lisp is, in general terms, it's a programmable programming language, and this will be a major topic of this presentation. Why it's programmable? So it's dynamic, so it has dynamic, strong, and gradual typing. So types are generally checked on in runtime, not at compile time, though as you will see later, compile time type checking is also available, and it's gradually typed, so we don't have to specify types of each variable or each function up front. We can do it like later, gradually, so we can define so we can basically prototype something quickly, don't specify any types, then we can optimize it by specifying them. So it's multi-paradigm, so you can do procedural or imperative programming like in every other major language, like, I don't know, C, JavaScript, whatever, Python. You can have functional programming, like, well, in its earlier form. Nowadays, functional programming is more focused on like complex type systems and such, but I will explain how Common Lisp also implements functional programming. And Common Lisp is also object-oriented. It's a major part of the language. So there is this misconception that Common Lisp is an interpreted language, but it's not true. It's like generally compilation or interpretation is not a property of the language itself, but it's a property of the implementation, unless something in the semantics prevents you from doing one or the other. But generally, even C can be interpreted if you really want. Like CERN has their own interpreter called Sint, I think. So, but generally you can both compile and interpret Common Lisp, so that's great. Memory management, it's funny, but it's not necessary. Like it's generally known as a automatic memory managed. It's generally known for automatically managed memory, but it's actually doesn't have to be that way. So the standard actually doesn't specify how the memory is managed. So some implementations can do manual memory management if they really want, and they will be standard compliant. But generally, Common Lisp is garbage collected, so you don't have to think about allocation of memory too much. And your implementation handles that for you. So we have one great thing about Common Lisp also is that it had multiple implementations from the start. It was initially designed to be implemented by different companies. So like initially those were Symbolics, Xerox, Carnegie Mellon University also, and such. And now there are open source implementations. So the most popular and my personal favorite is SBCL, or Steelbank Common Lisp, which is a compiler. There are also commercial implementations, mostly Lispworks and Allegro Common Lisp now. They're pretty expensive, so I don't use them. But some companies do, and they provide commercial support. You can buy maintenance contracts and such, so that's great. And so it's the language is actually defined by an American government. There is this American National Standards Institute, or ANSI. It defines multiple languages, not just Common Lisp, C, C++, Ada. So initially Common Lisp was requested by ARPA, or now DARPA, Advanced Research Projects Agency in the United States. There were multiple variants of Lisp, and they wanted everyone involved to converge on one language. So they insisted, they asked really strongly to come up with the single language, and this is the result. So this happened in 1982, and then the actual standardization process was very long. There were like 3 major versions, and the final version was ratified in 1994. So it's pretty old, but it's not generally a problem. Just something to keep in mind, that it's a fixed target. It doesn't change, unlike say C++, which gets new versions every few years and gets bigger and bigger. Common Lisp is already as big as it gets. So it's important to know that it's this direct descendant of the language called Lisp that was invented by John McCarthy in 1958. And Lisp is the second oldest programming language still in use in some form. The oldest is Fortran, and Fortran is mostly used by high-performance computing physicists and engineers. But Lisp is represented now primarily by Common Lisp. Some argue that really it's the only Lisp right now, along with Emacs Lisp, and Scheme and Clojure are not Lisps, but well, it's a very difficult holy war, so to speak. We're not gonna expand on that. So yeah, it is directly derived from that original language, which invented a lot of things at the time. And the main designers of this Common Lisp is so-called, not sure how to pronounce it, Quinquiverate. So Guy Steele, Scott Fellman, David Moon, Daniel Weinreb, and Richard Gabriel. So yeah, this is Guy Steele with the second version of Common Lisp in his hands. Yeah, I have this book. It's Common Lisp, the language, second edition, and around him other books he worked on. So he also worked on Java, and he wrote a book about C and Fortran and Hacker's Dictionary, which is pretty cool. So yeah, very prolific person, made a lot of things. So yeah, and so he worked on this ANSI document that defines the language. You can see its proper name on the screen. It's very difficult to memorize, and this document costs money, and generally people don't bother to buy it. and I've heard it's actually a bad, like what you can get on the site of ANSI is a badly scanned copy, so don't bother. Instead, we have the draft version of the standard, which is pretty much identical to the final version, and it's available online. And there's also Common Lisp Hyperspec, which is a web version, hyperlinked version of the specification that is proprietary but available for free for anyone to use, and it's primary reference for most people. Then there is also so the ANSI document doesn't really fully define the language, so there is also the book called The Art of the Meta Object Protocol. I don't think I brought it with me. Yeah. So yeah, this is the de facto standard for the thing called Meta Object Protocol, which allows to expand the language further. I will go into more detail about that a bit later. So you can see the cover on this slide. So it's not part of the ANSI standard, but it's the de facto standard, and most implementations try to implement it as well. So yeah, so now we're going to talk about the language itself. Syntax is the first thing you see when you start learning the language. So it is very simple and uniform. So you can see the simple recursive definition of this Common Lisp syntax. So everything is a form. A form can be literal, like a number or a string. It can be a symbol, which is basically a name for something else, like it's called identifier in other languages, but we're going to go a bit deeper on that a bit later. And forms can also be lists, which are basically a bunch of other forms. So so if it's a list, then the first member of this list is usually a symbol. Well, actually, it's always a symbol. And then everything else can be any other form. So we have lists of lists of lists, so they can be nested as much as you want. And you can see this diagram. I took a photo of from Node manual. I didn't want to make it myself. So you can see the operator on the left. Well, in this case, it's the plus function that adds numbers. It's surrounded by parentheses, and other members of this form are other lists. So first operand is also a list, and the second operand is also a list, and they have the same structure. So the first part of the list is also an operator, a symbol, and then there are two literals, 2 and 3 and 4 and 5. These are literals, and plus and asterisk are symbols. They refer to functions. So this is how we write comments. So they can be either single line with semicolon, or they can be multi-line. So they're not really part of the semantics. They are completely ignored, but we can use them. And this is the important concept. It's called quotations. So everything here, so forms when the language is so when our source code is actually executed in some way, this process is called evaluation. So it can be compiled, and then the compiled code can be executed by a processor, or it can be just directly interpreted. And so evaluation goes, so you feed a form into evaluation and it returns some other form. And we can control this process. We can use a form called quote that allows us to turn its operand into a literal. Another way we prevent it from being evaluated. So when we evaluate a quoted form, it just returns its operand. So this is the importance of this will become more obvious later, but for now I just want to introduce the whole concept. So we can evaluate forms and they return other forms, and some things we evaluate they just evaluate to themselves. So these are called literals. So when we evaluate a number, we get a number in return, the same one. If we evaluate a symbol, we get the meaning of that symbol. So it can be a number or any other form that was assigned to this symbol. Or if we evaluate a quoted symbol, we just get the symbol itself, not its meaning. So we can prevent things from getting evaluated, and so this way we can operate on symbols instead of just getting their meaning whenever we encounter them. And so this is how it looks like on the slide. So if we just have a symbol foo, when we evaluate, we get the value of foo. But we can put it inside a quote, and then when we evaluate quote foo, we just get foo instead of the value of foo. If we evaluate this list plus 1 and 1, we get the result of this of the evaluation of this form, and it's 2. But if we quote this list, we just get the list itself, not what it means. So it separates you can say that it separates the form and the meaning of things, the form and the essence. And we have a shorthand for quote forms, so it's just a single quote like this one, and we can use it to quote things more quickly instead of writing quote every time. So now we get to our basic data types. So there is this widespread misconception that Lisp only has lists and nothing else, but it's very, very wrong. We have a lot of other data types, basically what you have in every other language. So, well, with the exception of symbols, which are, well, are we running out of time?
I think we have 20 minutes.
Oh, yeah, I guess we will have to break it into parts. Yeah, we will have to break it into parts. So, yeah, so we have multiple data types, symbols, numbers, characters, sequences, and hash tables, and structures. So there is a complex hierarchy. So the symbols are names for things. They can be, so we have special symbols nil and t, which so nil means either, so it's can be a boolean also, so it means false, or it can also mean an empty list. And t is basically a boolean, it means true. Then we have numbers, integers, ratios, floating point numbers, and complex numbers. Not every language has complex numbers, I guess. And also the same thing can be said for ratios. So when you divide a number, usually in Common Lisp, like you divide 2 by 3, you don't get normally a floating point number, you get a ratio, which you can convert to floating point number. So you can operate on ratios, and the standard library supports that. and you have complex numbers, and the floating point numbers in the standard, they are not what you are used to now, IEEE standard. This is undefined, but implementations usually provide IEEE semantics. So we have characters and the literals for these characters in syntax look like this. So sharp, slash, and then our character. And we have and for white space and other special symbols, instead of just one single character, we can write the actual name of our special character, like space. Then we have sequences, which can be conses and arrays. Conses are basically the most general type of, well, it's a building block for lists in Common Lisp. So it's a pair of values. They're called char and cadr, and in Common Lisp they look like this, as you can see on the slide when they are printed. So they are separated by the dot, and you have the functions that are named the same way that allow you to extract the char part or the cadr part. And the function that creates this pair is called cons, hence why they are called conses. And also like allocating memory in Lisp is also usually called consing because of that. Because initially it was creating new pairs in the memory that refer to other things. Then conses can become lists. So if we put these conses into a chain, like on the slide, so you can see in the upper right corner we have a simple list that consists of 3 numbers, and so it consists of 3 cons cells, and the cadr of each console points to the next console in the list, and the last one, the last cons in the last cadr in the last cons of the list has to point to an empty list or new to terminate. So this is the main difference between cons and lists, is that they're usually new terminated, and so when they're new terminated, there is no dot in the printed form of the list. So you can see this on the slide. And then we have multidimensional arrays. They're more specific form, one-dimensional form called vectors, and vectors of characters are strings. They look like this. Then we have hash tables, and we have structures like in other languages. So let's get procedural. This is procedural programming. We can define functions with defun. We specify the name, the arguments, and then we have an arbitrary number of forms as their body. We can define global variables with defvar. We specify the name and the value. We can define local variables with let. And then we have, as you can see, a list of pairs of names and their values, and then we have the body, which consists of multiple forms, and then we can set both types of these variables with set f by specifying the name and the new value. And then we can call the functions we defined by having this form with the name of the function as their first member, and then the arguments. So this looks like this. Here we define the variable called foo. We usually have this convention of putting asterisks around global variables. so we can easily tell them apart from local ones at a glance. So we define a variable that equals 42, then we define a square function that multiplies it on itself like this. So argument x, it gets multiplied on itself, x on x, then we call this function on our variable foo, and we get the result, 42 multiplied on 42. Then we changed our global variable, set it to 3, then we call the function again, and then the value that the function returns is 9 instead of 1764. And then we define another function. We can see multiple, so we can see here we have multiple arguments this time, and we are using let to define a local variable called bar, which is equal to 1337. And then we call multiple forms that call function format that prints our string and a number, and then we print the value of this local variable bar, which you can see the result, and the result of calling that function you can see below. So we can have more than this, we can have more kinds of arguments, more than just the required ones. We can have optional ones. So we have this special, when we define a function, we can put this symbol in our argument list called ampersand optional, and then any arguments after that are optional. And so we can have function with one required argument and one optional here as an example. If we call less than that or more than that, we get an error. And then we can have named arguments that come after. Oh, okay, so I'm sorry, we have to finish up for today. We will continue next time in part 2 from the same place. Thank you everyone for participating in our meetup and for watching this presentation. So this is the end, I guess, because we ran out of time in the library. So yeah, so thank you everyone again, and goodbye.